Yeah. Good morning again. I show you a little video about Oxford.
It's possible to spend 24 hours without thinking of Oxford, but it's harder to avoid our work. If you're standing up again, if you're eating in a hurry, if you're under the weather, interested in the weather, or have suffered from its effects. If you're worried where your lunch came from. If you use a phone, a computer, or possibly a car. If you listen to the radio. If you use the English language. Or if you've seen it used rather well. You might also find us on a night out. Or an early night. But wherever you've encountered us, you can know we're dreaming up more ways to put our research to good use.
Our marketing guys are doing the best to remind ourselves how important it is to give us good research funding, because obviously in the changing nature of our funding sources quite it's my pleasure to share this session together with my colleague Ben Goodstein. I will be doing the boring theoretical bits, and Ben can show you that he actually knows what's going on under the hood. The session is a revision of what we've done at Mac sysadmin in Gothenburg last year. And we want to think about how we can use certificates to replace our key source of pain passwords. But to start with, I want to make sure that at least you have one takeaway, which is at least a solid understanding of the basics of cryptography. And I have to use these slides again because it took me days to click them together, and I will milk this as long as I can. So we have Bob and Alice, and they're good friends, but they don't want all the other friends out there to hear what they're communicating about. So to do this, the most easy way is to use symmetric encryption. Symmetric encryption means that Bob decides on a key, a password, and then he somehow gives that key over to Alice. And then both are aware of the password, and Bob can take his message, encrypt it with that password, send the encrypted message over to Alice, and as she is in possession of the key, she can decrypt and read the message, and over the transport, whatever that might have been, that message was secure. However, there's that challenge, how to exchange that key. Because the key, Alice might be, in terms of distance, on a different continent. Yeah? There might be geographic distance. There might be obstacles for the secure key exchange. So to fix this, we have to think about, we get this key transported. And there's a solution to that, which is applied everywhere nowadays in simple stuff. Like, for example, if you browse a TLS encrypted website, on the right-hand side, you see here an animation of the Diffie-Hellman key exchange. And it's running at fast speed, and it's continuously playing, so the video will start again. But it's a lot of modulus arithmetic involved. I will not explain that. There's a YouTube video. It takes 29 minutes, and it explains it very, very well, which is linked there on the bottom of the slides. But the Diffie-Hellman key exchange allows you to exchange a key in public, very secure. However, this fine gentleman, James Henry Ellis, worked for what is now the British GCHQ. So there are some good things which come out of intelligence. It's what was actually part of the post office in these days. And he came up in 1970s with something which is called non-secret encryption, which we actually call nowadays more like public key cryptography. And here are we. It's again Bob who wants to send the message over to our friend Alice. But this time, Alice has a lock. And Alice takes that lock and she keeps it open and she sends it over to Bob. So Bob can take his message and encrypt it with the lock. So the open lock was used to close the message, but Alice is in possession of the key because he never ever had a key. So with the key, she will be able to unlock it, and she gets back the plain text, the message. Does that make sense? So there was no key exchange. And so to do this again, the lock is the encryption key. The key is the decryption key. And the decryption key can be shared in public because it can only do a one-way function. It can only encrypt. There's no harm to give people something with which they can encrypt something because nobody's in possession of the inverse, which is the key to decrypt. So Bob can use the encryption key to encrypt his message, securely transport it back, and then, as already mentioned, the key does the inverse, so it undoes the encryption, and there we go, we have the plain text again. So the problem of key exchange has been thereby eradicated. So to look at this in a more simplistic way, I want to use the example of all these Mac admins being just designers. We know nothing about technology, but we like colors. So I apologize for somebody being colorblind, and I thought about this a lot because at the last talk I had, unfortunately, somebody couldn't see the colors, so I tried to repeat the colors, but it doesn't work with shapes. I thought about it, but it doesn't really work. Here, in this example, Bob and Alice have eavesdropping Eve, and Eve will see everything that goes over the public channel. So everything that goes from left to right or right to left will also be seen by Eve. So always draw attention what also ends up with Eve. So Alice has chosen a favorite color yellow, and she wants to send it over, and without encryption, Eve gets it. So let's come up with a few assumptions that the example works. Theoretical foundations of this really hard, colorful talk. But we're thinking about light. And light is an additive color space, as you all know as designers. And every color has an inverse. Here we have red and kind of cyan. And mixing these additive colors, if they're complementary, perfect, it undoes the effect of the other color. So white light. Does that make sense? Easy. And now we have to introduce an invariant which says mixing is easy, but decomposing the two colors that are used to mix a color is incredibly hard. We can't solve this with current technology. So please stick with me for the next 10 minutes on this example. So, and now Bob can choose his favorite color, red. And what he does, he says, red is my private color, it's my favorite color, I don't want to tell it anyone. And he sticks it in his super duper secret color matching machine, and the color matching machine spits out the perfect complement, which is our sign. And together, they again do the inverse of each, so they're white. So that machine gave him these two colors, and now Bob says that complementary color is sent over to Alice. Obviously, it was sent over in public, so Eve gets notice of that. So now Alice can take her favorite color yellow, which is her secret, and she can mix that with Bob's public. And the color was yellow, and it was mixed with the blue, so that gets green. So green is here the perfect mixture of Bob's public and Alice's secret. And then Alice can send that mixed green back over to Bob, but as that went over the public medium, Eve got the green again. However, Eve just had these two colors, and if she mixes them, she ends up with a lighter bluish cyan color. But Bob is in possession of the complement of the color which went over public, which is this red. And by mixing the green with the red, he gets because the red does the inverse operation of the mixing with the blue, he gets back Alice's yellow. You're really quiet. Don't like colors? Does that make sense?
Yes.
Okay, I have to do it again because I really like these slides. Okay, so this is how asymmetric public-private key cryptography works. That's all of it. We have a private key and we have a public key. And both keys can encrypt, and the other key can do the opposite, it can decrypt. So it doesn't matter which one we use, but only the person in possession of both can do both operations. And this is why we keep one very, very secret, that on the other hand, the person can either encrypt and I will be the only one to decrypt. That's what we just have seen. But there are other use cases, which we get to in a second. So this whole thing was invented in 1977 by Rivers, Shamir, and Edelman. They introduced the algorithm in 1977. This is why it's called RSA. However, a certain Mr. Clifford Cox, again an English mathematician, working for GCHQ, developed the same thing 3 years earlier, but it was deemed classified. So unfortunately, these guys get the thing. So now we're doing the inverse. Again, Bob has his private red, he has his public green, and now we want to send the color over to Eve, here, public red, private sign, and we have a green. And we want to make sure that this green arrives with Alice, and she knows that it was definitely Bob's green. So what we do is we now encrypt with the private key. So we mix now the red with the green, we get again the yellow. I was a bit lazy on choosing colors, I'm sorry. But now we can take this yellow and set the yellow over to Alice. Yeah? If Eve would be there, she would have seen it, but no harm, because the private key stays on this side. And the interesting thing is, Alice is in possession, obviously, of Bob's public key. And the public key can do the inverse of what I've done with the red. So she can decrypt that. Yeah? So she can get exactly the right color. And on this principle, that if you encrypt with the private key, and people can use the public key to decrypt, we can build signatures. And signatures nowadays are everywhere. And Ben will give a couple of examples where signatures are being used and useful. So let's make this as an example with a document. Here we have the message. And what Bob does is he computes a checksum in cryptography terms digest. Yeah? SHA-256 is probably what we use nowadays, MD5. Now there are a few collisions known, maybe we won't use that. So, and he takes that digest, the checksum, and he encrypts that with his private. And the encrypted checksum, the encrypted digest, is the digital signature. So now he can take the signature and the original message in plain text and send this over to his friend Alice. And Alice is in possession of the public key because it's publicly available. It might be in that little bundle. Plain text, the encrypted signature, and the public key. So now Alice has the 3 tools with which she can verify, is that really the message I should have received? Because she can first compute the digest herself because she's in possession of the plain text and she knows the algorithm. So Bob used SHA-256, I will use SHA-256. Now she has the digest. And then, because she's in possession of the public key, she can just decrypt that. Oh, sorry, that was too fast click. She can decrypt that. And then she has the decrypted signature. And with the decrypted signature, she can compare these two. And when she compares them, they're equal. She knows, yep, the message is the original message I should have got. And that's how digital signatures work. Does that make sense? Are you asleep? Are you playing with FileWave? Okay, so it's really, really important to understand that whatever we do, we have to choose the key we do our operation with wisely. And one key has to be extremely protected. So what do we do with these signatures? We create certificates. And we call this a public key certificate. And it's typically just to prove that somebody owns the public key. It's really just proving, yep, I'm the owner of this public key. And let's look at the anatomy of a certificate a bit more in depth. So this is a certificate which has the public key in it. There is the signature, yeah? And then it has a reference to who signed it. There's also other information in it, like how long is it valid, and so on. But this information is all additional stuff, and there are even interesting extensions which say, what can you do with the certificate? Can you encrypt websites, traffic, or can you sign emails and other stuff? So let's look at an example. Apple website, I'm browsing it via HTTPS, so HTTP over TLS. Please let us not use the word SSL anymore. And the certificate is apparently verified by Semantic Corporation to be owned by Apple. If you look at the details, we have here a blue standard certificate, again issued by that company, Symantec, and it expires in a few months. And we can even look more into the details. It has been issued by Symantec for the common name of www.apple.com for that website. You get more information, location of that organization, and so on. But the most important thing here to look at is that it has been signed by that Symantec corporation, issued by Symantec Class 3 EV SSLCA, up here in the top. And if I now click on the certificate chain or the certificate on top, I will be exactly looking at that certificate. And this certificate has this name, and it's an intermediate certificate authority. And this intermediate certificate authority was again issued by the VeriSign Class 3 public primary CA, which then is the one on top, as you can see in the top. And this is now a different certificate. That's a root certificate. So this one needs to be especially protected in terms of the private key, because with that one, Symantec issued the intermediate CA. With that one, then they sign all the individual certificates. And the certificate chain is always really important to keep in mind, because the root certificates are obviously what is distributed into a lot of systems by default. Our browsers, our system keychain on a Mac, our phones, they will all have just a very few root public certificates, in their embedded, and those will define what our systems will trust and not. Just to show you that I actually from time to time know what I'm doing, I put in a little screenshot here. So this is the output of OpenSSL client. So I'm connecting now with the OpenSSL command to Apple, and I get exactly the same information. I get that certificate with the common name www.apple.com up there in yellow. And there's the intermediate certificate in green and the root certificate in blue. So I can look all of this up very easily and can use this programmatically. There's more content with that. So where are these root certificates visible? You open keychain access and you click on the left column into system roots, and there you will see a lot of interesting ones. I don't know, the German would make a joke. Turk trust, I don't know if I would trust them. Nonetheless, there is a rule how to get in there, and Apple has published that, www.apple.com/certificate authority. And Apple has set up very, very strict standards which you have to comply with as a certificate authority to be added to the root certificates. Quite interesting read, a lot of conditions, really dry stuff, but it shows that there is a lot of work to be done there, and there are a lot of certificate authorities which have done a lot of bad stuff. Public key infrastructure requires a lot of things. So somebody who is the certificate authority to store and issue the certificates, somebody who actually verifies that new certificates that should be done are correct and then deals with that. And probably most importantly is you need something like a strict policy. PKI is a complex topic, and you see that the big companies really care about this, like Google has just acquired 2 independent CAs to jumpstart their own one. So to close my bit of the talk, if you want to create a CA, OpenSSL, the open source implementation of all of that, delivers a tool called ca.pl. The man page is, again, in the lecture notes, but we can quickly do this with keychain access. If you go to the keychain access main menu, there's a certificate assistant, and it has a lot of options. So if you click on create a CA, it will pop up a dialog. You just stick in the name of your CA, what you want to do with the certificate. I chose here SSL server. It's actually not that relevant for the root CA, and an email address. You can give it a serial number because you might want to renew your CA. You can make it valid. For testing, a year is more than enough. If you want to use this in production, you probably want for the root CA more something like 10 to 20 years because replacing that is a lot of work. And there you go. You have a CA, and then you have a couple of files in the file system, which is the public bit. So this is the certificate key and a bit of config, and the actually the private key is in your keychain. Then I can request a certificate. Here we request a certificate for the common name webserver.acme. I can then save this on my file system, or I can email it directly to someone. So I say I want an RSA 2K key. Please go for nothing else than RSA 2K at least. If you want, you can go for 4K. And then you get your certificate in your keychain, and you get a certificate signing request which you can email or store. So with the certificate signing request, which we're seeing here, we actually have, again, the email address and the common name, and there is my public key. Yeah? And then this whole thing is signed. And this I can then give to my CA. So the CA, sorry, the CA, here the issuing CA, imports that certificate signing request. I did this again with keychain assistant, issue a certificate on behalf of someone as a CA or something like that. I choose my CA because I'm pedantic. I click through all the individual options. This certificate will be valid for a year. I can even override the information I've been given by the webmaster if I want to. And then I can choose what the key shall be used for. And this one should only be used for signature, and to be more precise, SSL server authentication. Okay, I'm done. I save this one, and there we go. There's my new certificate signed by my CA. Looking at that certificate very quickly, again, the OpenSSL command if you're interested. This is then with a version, a serial number, when it was from the validity period, and there's the public key again, and then here's the signature algorithm, and below it you would see the signature, which is then the signature from the CA for the checksum of that whole bit above. Last thing, certificates might get compromised. And to get rid of certificates, there's a system called certificate revocation lists. The certificate revocation list is published in public on a web server typically. This is Apple's own root CA, and I'm looking at it. This is version 2. It was last updated in November, and I downloaded this yesterday evening. And it has no revoked certificates. So nothing has happened to Apple's root CA. However, if you look at Apple's developer relations certificate revocation list, which has been updated very recently, there's a list of revoked certificates. How many revoked certificates? And the number has changed since my last talk. Come on, everyone, make your guesses. 17.
200.
200.
A couple of 10,000s.
Couple of 10,000s.
100,000.
Over 1 million.
1 million. I have 1 million. Give me more. Man, are the developers really bad? Okay, this number has gone down over the last 5 months. It was in October last year. It was 2.45 million. But this is because a lot of certificates expired, and not so many certificates have been issued. And this is why these lists are updated. So CRLs are really, really important. They're an essential part. They're more modern things, which I can't touch on because I'm already over time and then just getting nervous. They help us to assure that if a certificate has been compromised, like private key loss, then we can revoke it by adding it to the list. And we have to make sure that these CRLs are being checked. So that's it for me. Practical stuff. Talking stick to you.
Thank you, Marko. Okay, so everyone understands PKI cryptography now. I can get on with some demonstrations, and we'll be clued in. I'm going to choose 3 situations in which Mac admins might use certificates to improve their security or to manage authentication. And the 3 examples I'm going to use are secure MIME for email, how you might sign your applications and installer packages for Gatekeeper, and certificate-based authentication to a web server. Okay, so we start with S-MIME. S-MIME is a protocol which allows to secure email based on PKI cryptography. It uses certificates and keys to sign emails and to verify signatures, and it guards against emails being altered in transit. So it's about integrity of messages as much as the identity of the sender. And it also allows for the encryption of the email body. It's one of the few different applications for secure email. Others are available. There is PGP, GPG, there's even TLS to authenticate with your outgoing mail servers and so on. But in this example, I'm going to use S-MIME. Now, in the enterprise, it would make more sense for you to use a directory service and perhaps your own CA to store and distribute public key certificates. But there are certificate authorities who will let you create a personal email signing certificate and encryption certificate for free. And one of them is Komodo, which you can see here. They have a website which ensures your mail cannot be read by anyone but the intended recipients. And you can also ensure your message was not modified during transmission. That's what we want. That's what we're looking for. So here on their website is how you sign up for a certificate. You enter some details and an email address, which is where the certificate is going to get sent to. You have some private key options, once again, 1024 bits is coming uncomfortably close to what could be cracked given enough computing power these days. So always go for 2048 or higher for your private keys. And you can set a revocation password here, which would allow you to add your certificate to those CRLs that Marko was just talking about. So your certificate would be revoked if maybe your private key fell into the wrong hands, and then you could revoke it in this way, and then people would no longer automatically trust it. Okay, so the certificate authority, in this case, replies with a link to a .p7s file, which does not contain your public key, but will cause it to be created when you import it into the keychain. So this is what it looks like when you import into your keychain the file. You can view the certificates. Always a good idea to view your certificates. Never just trust things blindly. And here you can see, you go up the chain, which Marko described. So my certificate is signed by the intermediate, Komodo, and then that is signed by a root certificate, which is the root CA, AdTrust, which is automatically trusted by macOS. It's in the system roots. So that means if you use one of these certificates, if it's signed by that CA and that intermediary, it'll be automatically trusted by the OS. And here you can see in your keychain, you have both the public key certificate and the private key that you would use. Now, if the entire chain gets imported, and if the root CA were not trusted by the system, you would have to explicitly trust it here. But in the case of AdTrust, like I say, we're okay. So what does it look like in practice? Here I'm using Apple Mail. Different mail clients will implement S/MIME slightly differently. But here we show how to digitally sign an outgoing email. So if I click that check mark there, what Mail does in the background is it's going to use the signing identity that matches the email that the email address that is being sent from, and it will pull that out of the keychain and will sign the message. Okay, so here's what happened in the background. The hash of the message body was computed. The hash is then encrypted with the private key from the sender's signing identity. And this is attached to the outgoing message in what's called a PKCS7 signature, in the case of a clear signed message, or combined with a message which is known as opaque sign. Now, opaque sign messages where the signature and message are combined in one attachment are less likely to be mangled in transit by, say, mailing lists, which have a habit of adding things onto clear signed emails. So if you think if something gets added by a mailing list, it's going to be bad because you've said this is what the message contains. You've computed a hash. The mailing list puts like some footer on it, and then the hash is wrong. So, but the only problem is that not all S/MIME clients can read opaque signed emails, so they're not actually encouraged if you want to adhere to standards that everyone can use. Okay, so here at the other end, the email has been received, and you can see that Mail highlights that by showing you a security header, and you can see here that it is signed, digitally signed by that email, and if you were to click on it, you'd see the same certificate chain verification dialog that we've been looking at before. Okay, so what is going on when Apple Mail shows you that icon? So, the encrypted hash of the message body is decrypted with the sender's public key. Remember, you decrypt with the sender's public key. The hash of the message body is calculated by the recipient. The two hashes are compared, like Marko said, and if they match, the message was not altered in transit, and then it will display that icon in Apple Mail. Of course, encryption is also possible. Here I'm going to send a reply. But this time, I'm both going to encrypt and sign the message. So you can see there, it's demonstrated by highlighting the padlock as well as the checkbox that we used previously. Whoosh. Okay, so what's happening behind the scenes here? For S/MIME mail encryption, a one-time session key is generated. So a throwaway key is made. The message body is then encrypted with that session key. And then the session key is further encrypted with the recipient's public key. So at the other end, you can decrypt with your private key. The encrypted session key is attached to the message body and sent off as an attachment. And here at the other end, the message is received, automatically decrypted by Apple Mail, as the recipient holds the private key necessary to do so. And this, you'll note that security now shows encrypted. Now, the eagle-eyed amongst you may notice that it should say encrypted and signed, and it doesn't, and Apple Mail is really buggy about showing you this reliably. So different versions will do different things. So yeah, you can't always rely on Apple to put the headers in correctly. But if you create mail rules that depend on them being encrypted or signed to, say, color your inbox different colors, then that seems to work. So it's a little bit inconsistent. Okay. So what's going on when it shows the encrypted icon is that the session key, that throwaway session key that we were talking about before, is decrypted with the recipient's private key, and then the message body is then decrypted with that session key. Okay, so we're going to move on to Gatekeeper. So you're probably all familiar with Gatekeeper and its settings within system preferences. But in the background, it's actually using PKI identities to verify downloaded code and to protect your system against malicious attacks and modifications to code after it's been signed. Gatekeeper is actually the GUI front end of a command line tool called SPCTL, which you can explore at your leisure with man SPCTL. But basically it's macOS's mechanism to check the integrity and the developer identity of apps and installer packages. It runs on items with quarantine attribute sets, so things that you've downloaded from a web server will trigger Gatekeeper, and it will halt the execution of unsigned code or installers depending on your settings and system preferences. But Apple provides you with two tools with which you can sign either your application code, which you would use CODESIGN for, and that embeds the signature of the developer or signer into the application and ensures, once again, the integrity of the code that has not been tampered with since it was signed. And you can also use PRODUCTSIGN to sign installer packages, so PKGs. And by default, that also embeds a trusted timestamp, the validity of which is checked if you're connected to the internet. Okay, let's quickly look at CODESIGN. Okay, in this example, we've developed an app in-house that doesn't need to be installed from a package, and we've uploaded it to the company intranet to distribute to our users, but we have not signed it in any way. And you can see the mydodgyapp.zip. So that's obviously to be trusted. For those of you who are not native British speakers, a little explanation of the word dodgy. It sounds like my work ethic, dishonest or unreliable, potentially dangerous, and of low quality, or of low quality. Okay, so here I'm using the example of an application contained in a zip file, but it could just as easily be a DMG, a drag and drop install. As you can see, when we try and run the downloaded app, since our settings only allow applications from the Mac App Store and identified developers to run, Gatekeeper complains that it is not signed by an identified developer. So what can we do about this? Well, we can use CODESIGN to sign the app. So here I'm just first moving the app to a staging area before I sign it. Next, I use the CODESIGN tool to sign the app with the signing identity I have obtained from the Apple Developer Program. So CODESIGN will try and find the signing identity specified, so that's the Developer ID application University of Oxford, in the user's keychains, but you can optionally specify a keychain to use. Okay, and so when I run that, it will ask me for a password. I know this is towards fewer passwords, but in this case, this is the signing identity for the whole of the University of Oxford. It needs to be kind of protected, so it's behind a pretty secure password. And like that, the application is signed. And we can see those, in fact, those, hang on a minute. So Marko is such an egomaniac that he even is the name of our signing private keys for the university. So he's guaranteed to go down in history. When we're still using these in 100 years' time, Marko's name will be attached to everything that we sign. Okay. So now I'm just going to run a little script to copy it back up to the web server that I just downloaded it from. And I'm going to re-download the application from the web server. And this time when I go to run it, Gatekeeper does not pop up. Instead, it is the normal quarantine dialog. Gatekeeper has checked the application and seen that it's signed and is happy that it's met its requirements. And the application runs successfully once we have clicked open. And it does a huge amount, as you can see. Okay, so what's happened behind the scenes here? CodeSign has generated a signature from the signing identity and embedded it within the executable code. All of the resources within the app have been hashed. So that's the message digest that we were talking about before. And at the other end, when the code is run, Gatekeeper verifies the signature is trusted and that the resources have not been altered in any way. And here we're going to use CodeSign's verify option to mimic what Gatekeeper does when it examines the app. And you can see that it says it's valid on disk and it satisfies its designated requirement. But what's a designated requirement? Well, this is something that's automatically generated when you sign the app, but you can also specify different requirements that you want to designate to this app. So there are options that you can use when you're signing. But if we check with CodeSign display and we send the requirements to standard out, you can see the requirements at the bottom there that show that it needs to have the right identifier, it needs to have the right certificates in the chain, and they need to have the OUs that are listed. Now, those of you that use AUTOPKG, I may have seen in lots of recipes a processor called CodeSignature Verifier. And in the background, it's just using CodeSign for applications. So it's just verifying that those requirements that you set are matched in the application that you downloaded. So you can be sure that the application hasn't been tampered with and is signed by the people that you're expecting it to be signed by. And then there is PRODUCTSIGN, which is for installer packages. So maybe we decide that we're going to distribute this in a package now. We want to install files on the system. And so we run it. But Gatekeeper is unhappy again. Again, it's an unidentified developer. We haven't signed this package in any way. So again, I'm going to move the package to a staging area, to the unsigned folder this time, because PRODUCTSIGN creates a whole new signed copy, and we don't want to get them mixed up. And now I'm going to use PRODUCTSIGN to sign the package, this time using the installer ID, not the application ID, but the installer ID. There were two IDs. And again, I have to put in my secure password. Password 1, 2, 3. And then I copy it back up to the web server. And re-download it. And the installer runs this time. And you'll see this padlock in the top corner. And there you can see that the chain has been embedded into the installer itself. I can run through and install the app. And the app is happily within my application, so you can't see popcorn time or anything in there. So. There we go, a dodgy app, running again. So what's happened here? PRODUCTSIGN generates a signature from the signing identity, and it embeds it in the installer package along with an optional trusted timestamp. And at the other end, Gatekeeper verifies the reverse. It verifies that the signature and timestamp are trusted before allowing the package to be installed. Okay, so you don't actually use PRODUCTSIGN to check package signatures, you use package util. And this, with check signature, it tells us that the package has been signed by a trusted certificate macOS automatically trusts those signed by the Apple Developer Intermediate CA and prints out some fingerprint information we can use to check against known certificates. And again, AUTOPKG code signature verifier uses the same mechanism, package util check signature, to check the authority names of the embedded signatures, certificates. Okay, finally, just want to quickly look at client SSL authentication. So what's this? This is probably the biggest example where we are actually mitigating the use of a password. So it allows web servers to verify that clients connecting to it have a certificate that is signed by a trusted certificate authority. And you might use basic authentication on your web server to protect certain important or sensitive parts of the web server. Instead, you can use certificates to obviate the need for entering a username and password. So if you set that up in Apache, the web server must be configured to serve outgoing SSL and TLS content, so it must be set up as an HTTPS server. It must be able to read the public certificate or the desired certificate authority from disk, and then you put in a directive into the config to either secure the whole server or a single location. So just starting out with the Apache web server configuration, I'm just going to SSH into my web server, and I'm just going to show you the config. Apologies for the typing here. Just have some background music for these. Okay, and I can just show you that. So this is where the CA is listed that we're going to trust. And this is where we say that we want to verify the clients. That's the second one. And this is inside a protected directory on the web server. So we're going to require that it verifies the clients using SSL. Okay, so let's say my boss has told me there's something really exciting in the protected area of the company intranet. Don't know what that might be. First, you can see that I can get to the root of the web server normally. It's a boring Debian holding page. But when I try and go to the protected area, it asks me for a certificate, and I don't have one. So what am I going to do? I can't get in. Do I cancel? Do I continue? Does it make a difference? No. Okay. So I'm going to need to request a certificate in order to access this site. I'm being told that I need to request one from the company's CA. So I can do that again in keychain access, as Marko showed you before. And I am requesting a certificate from a certificate authority. And this is going to create a CSR. So a certificate signing request. And this is just for me personally, rather than a web server. Okay, I don't need to show in Finder because it's there. And now I am going to sign that CSR, because conveniently, I am also the CA. And I am going to, using the create a certificate for someone else as a certificate authority short option. And I just drag the CSR in. I override the defaults because I do want to specify, this goes a bit quickly, but I definitely want to specify that this is used for SSL client authentication. If it's not, then you will still get blank certificates when you try and visit this web page. Okay, and now the next time I go to protected, it's there, and I can view it, and I can check the chain, and then if I continue, and then I just sign with my private key, I get to the amazing protected bit of the website, which seems to be the worst website in the world. Don't know if that was worth it, but yep. So just to recap, when SSL verify client is set, the client must sign its web request to the server. It happens as part of the SSL handshake that goes on between the client and the server. After the client has said that the server is okay, the server can request a certificate from the client. So the certificate must be trusted, must be valid, must be signed by a recognized CA. But clients don't have to be people. So management servers like Jamf Pro use client SSL auth to encrypt to authenticate the communication between the computer and a web server. Monkey can also be configured to use client SSL auth instead of basic auth, so you can revoke certificates, for instance, for people that leave your company, and you don't have to worry about them still knowing the basic auth password. Okay? And this is just further reading, if you're interested. And thank you very much.